Hey everyone, in this video we're going to find the equivalent mass of a system. Last time, or rather just in another video, we said that the reason why we might want to find an equivalent system is so that we can calculate different properties of the system without having to deal with the entire complexity of it. So for example, the natural frequency of the system would simply be equal to the equivalent stiffness over the equivalent mass. If you didn't reduce the system to a 1 degree of freedom system like this, then it would be much harder to do it. Okay, so what we're going to do is we're going to use the energy method, and to find the equivalent mass we're going to take the sum of all the kinetic energy terms in the system. So the first part to that is we're simply going to number the different elements that we have to include in our kinetic energy equation. So we have the mass, we have the rotation of the pulley, we have the rod rotating around this guy here, we have the rigid link, which is moving in the same direction as x2. I'll remove that. And then we have number 5. It's a cylinder, not a pulley, so we're going to have to find a way to calculate its moment of inertia. Now here we neglect the stiffnesses because I did another video that shows you how to calculate the equivalent stiffness. So here we're just going to focus on the equivalent mass. Step number 1 is that we're going to express all coordinates in terms of x dot. That's arbitrary. We could have used theta p, or actually this is theta p and this is theta c. Now we're going to use x dot. That's what I chose. Doesn't matter what you choose, but yeah, the reason why we want to do this is that we want to reduce this to 1 degree of freedom. Meaning, can all the other degrees of freedom, as in theta sub p or theta sub c, can be expressed as a function of another degree of freedom, then in reality there's only 1 degree of freedom. Okay, so we're going to start with let's say theta p. Well, you know that if we use the arc length equation, arc length equals r theta, you could say that x1 is this guy, x2 is this guy, is equal to r sub p theta p. But what we really want to do is express theta p in terms of x1. So theta sub p is equal to x1 over rp. Cool. What about x2? x2, really what it is theta p times L1. It's the arc length of this curve over here, this guy. So let's say theta p L sub 1, L sub 1. But then we want to express x sub 2 as a function of x sub 1, so we're going to substitute theta p for this expression over here. So what we get is L1 over Rp is equal to x1. Okay. What about theta c? Well, let's say that, let's use the arc length formula again. x2 is equal to theta c rc. Okay. Theta c is equal to x2 x sub 2 over RC, and then we're going to substitute the expression that we found for x2 in here. And so what we'll get is L1 RP RC X. Okay, so good enough. Now let's start calculating the energy terms. Actually, I will copy this guy and move it around so that it's easier for us. Okay, so kinetic energy 1, that's the kinetic energy of the mass. Well, that's simply equal to 1/2 times the mass. We will note it, yeah, just m, mass times x dot sub 1 squared. It's easy enough. The kinetic energy of the rotating pulley, well, that's equal to 1/2. We say we had that the moment of inertia of the pulley is J sub p times theta p dot squared. But we also knew that theta p is equal to x sub 1 over rp. So let's substitute 1/2 J sub p x dot 1 rp squared. So that's equal to 1/2 times J sub p divided by rp squared, multiplied by x dot sub 1, I forgot it here, squared. All right, number 3. Number 3 is the rod, the first rod. Okay, that one's going to be a bit harder because it's not rotating about its center of gravity or center of mass. So it really is the moment of inertia about 0 of the bar times theta p squared. So let's make a side note. J sub 0 3 is really the moment of inertia about its center of mass plus its mass, which is m sub 1, times the distance between where it's rotating and its center of gravity. So just to illustrate, it's rotating around O, and its center of gravity is at L over 2 if this is L and the mass is uniformly distributed. Now this is called the parallel axis theorem. And we use it to shift the moment of inertia from the center of mass to 0. Okay. Whoops, I won't let you peek at the answer. Should have deleted it before. Okay, so the center of the moment of inertia of the rod about its center of mass is 1/12 times its mass times its length squared. That's the moment of inertia of a rod about center of gravity plus its mass, and d is L sub 1/2 squared. So we can write that kinetic energy of the third element really is 1/2 times 1/12 mass 1 L1 squared plus 1/4, because it's 1/2 squared, times mass 1 L1 squared. And I'm going to bring this down a bit because we can't forget the theta term. And we said that theta p is equal to x1 over rp squared. Okay, so that's equal to 1/2. 1/4 plus 1/12 really is 1/3 m1 L1 squared over rp squared times x dot sub 1 squared. Alright, that was a bit of work. Now the fourth term, or the fourth element, it really is just a rod moving in the same direction as x2. So KE4 is equal to 1/2 m sub 2 divided by x dot sub 2 squared. And remember that we said that x sub 2 was equal to put it here, L1 over RP times x1, put the dot here. And so finally what we have is that it's equal to 1/2 times L1 squared M2 over RP squared times x dot sub 1 squared. Let's bring this guy down again. Okay, so the element 5 is the cylinder, and so since it's rotating and moving in translation, it has both rotational and translational energy. So meaning if you would want it to stop with your hands, for example, well, you'd have to stop it from spinning, and you'd also have to stop it from translating. So we need to consider both rotational energy. So we'll note that KE5 sub r, and that's equal to 1/2 times its moment of inertia. Let's call it JC theta dot squared C. Well, JC is the moment of inertia of a cylinder spinning around its central axis, and that's equal to 1/2 times its mass times its radius squared. So we have 1/2 times 1/2 m sub c for cylinder and r sub c squared, and theta c is equal to L1 over RPRC times X1. So L1 RPRC X1 dot squared. So that's equal to 1/2 RC will disappear because it's squared. And so we have L1 MC RP squared. L1 is squared also. X dot sub 1 squared. So translational energy KE5 sub T. Well, that simply equals to 1/2 times the mass of the cylinder times x sub 2 squared, and that's 1/2 times MC times, we said that x sub 2 is L1 over RP, x1, L1 over RP, oops, x dot 1 squared. So what that is 1/2 times MC L1 squared over RP squared. Yep. Times x dot 1 squared. Okay. So the kinetic energy of the system is equal to the sum of all the terms. So kinetic energy terms, so KE1, KE2, KE3, KE4, KE5 rotational, and KE5 translational. And that, I'm going to be lazy and just copy paste them. So number 1 is this. Plus number 2 is this. Number 3, where are you? Here. We're going to move all of this to the left so that we have enough space. Okay, so we have number 1, number 2, number 3. We're looking for number 4. Number 4 is this guy. number 5 rotational is here. So we're going to move it to the left even more to accommodate our last term, which is the translational energy of the cylinder. Almost didn't have enough space. Okay, so quickly we're going to factor this out. 1/2 times m plus jp over rp squared plus 1/3 m1 L1 squared over rp squared plus L1 squared m2 over rp squared plus 1/2 L sub 1 squared mc rp squared plus mc L1 squared over rp squared. All of that times x dot sub 1 squared. We can do more. So that would be m plus jp over rp squared plus, let's put, no, we can't do that. Yeah. These guys together. One-third m1 plus m2 L1 squared over rp squared. You don't really need to do this during an exam. Really, I never spent, or rather wasted the time to do this, but since I started, I'll finish. We have a half plus 1, so that's 3/2. Let's put this together. It's 3/2 L1 squared mc rp squared. So let me just make sure, yes. Third. Yeah, okay, yeah, that's good. And you know that this is equal to 1/2 times the equivalent mass times velocity. So the equivalent mass is equal to this. Now I know that that was long and tedious. When you do it, make sure that you take your time because it's very easy to make a mistake. And really, once you know how to do this, then really these are free points during an exam. I'll put the PDF worksheet in the description. Thanks for sticking around.